So hello everyone. So welcome to the regular Bootstrap weekly seminar, and it's a great pleasure today to have Ashley telling us about S-matrix Bootstrap related things, or more precisely, how to measure S-matrices. So Ashley, please.
Hi, I'm joined today by my colleague here, the squirrel on the tree behind me. Yeah, I'm very happy to be here. Thanks for the invitation. This is joint work with the grad student at Caltech, Jenny Liu, and John Presco and Guifrey Vidal. Guifrey, of course, being at an Alphabet subsidiary these days. I'm not sure which one. So without further ado, let's talk about collisions of false vacuum bubble walls in quantum spin chains. So the false vacuum scenario is one you may be familiar with. The idea is fairly simple. So you start, let's say, with a system that has multiple vacua. Say there's spontaneous symmetry breaking. It might be a Z2 symmetry breaking. So there are two different vacua. So this diagram is showing some effective potential for some field in a quantum field theory, let's say. And there are two wells, and both of those are equally good vacua for the field. Now, if the symmetry is explicitly broken, say by adding a field that causes one of these vacua to have a larger energy than the other, then in some cases, we can talk about there being a false vacuum. So a false vacuum is a metastable state, let's say, that has an energy density larger than the true vacuum. And for whatever physical reason, you might find that your system, say our universe, ends up in a false vacuum state. And if you're in a false vacuum state, then eventually you might expect some tunneling event, say, to take you to the true vacuum. So in this case of an explicitly broken symmetry, if you start in the false vacuum, maybe you'll tunnel to the true vacuum at some point. But in a false vacuum setting, metastable means that these tunneling events are extremely rare, and that for the most part, you just continue in the false vacuum. But if there is a tunneling event, then what happens is that a small, typically we consider something local happening, such that a small bubble of the true vacuum forms in some region of space. And because the true vacuum has a lower energy density than the false vacuum, well, the bubble starts to expand, the walls rush outwards, and eventually the entire false vacuum is eaten up by this bubble of true vacuum. Now we're going to consider a situation where you could imagine you have two true vacuum bubbles, two different ones at different locations, and they both start to expand, and at some point the walls of the two bubbles meet. So there's false vacuum in the middle and true vacuum on the outside, and the walls meet, and some energetic event happens when the walls meet, say particles are produced. And we want to take a step towards characterizing events like this.
Can I ask a question?
Yes, of course.
So is there a unambiguous, like non-perturbative way to define what we mean by false vacuum state? Because typically, like the pictures like these are like, when you're given Lagrangian description and we talk about, say, some classical potential.
Right,
and
right.
Yeah, we compute this type of tunneling using, say, things like WKB. But I wonder if, like, in fully non-perturbative QFT setting, let's say, if there is an unambiguous definition of what we mean by false vacuum.
Well, I think that's a really good question. Unfortunately, I don't know a full answer to it, but I do know that in the spin chain situation that we're treating, we can find a state which has like properties you would expect of a false vacuum that is, at least for all practical purposes, an eigenstate of the Hamiltonian. So it's not really even, maybe it's not even really fair to say it's metastable if it's an eigenstate, but you could still tunnel from it to the true vacuum if certain observations were made, potentially. But anyway, so in our spin chain situation, at least, there are eigenstates which can be thought of as being in the false vacuum sector, or at least good enough approximations to eigenstates that it doesn't matter for our numerics. And so we choose an eigenstate of the Hamiltonian that we call the false vacuum state.
I see. Thank you.
Okay, so people have done computations based on the standard model, assuming that the standard model describes the universe we live in. Then apparently there are reasons to believe that we might be in a metastable state and not in the true vacuum state of the standard model. Or, so then you might worry that actually this would happen in our universe and some bubble of true vacuum might form somewhere. And we won't see it coming, of course, because the bubble walls rapidly accelerate as they eat up the false vacuum and approach the speed of light. We wouldn't see it coming before we were engulfed. But it's, it's interesting to think about these situations, and it's also possible that such events were part of the evolution of the early universe. You can imagine that there might have been a false vacuum state early on in the evolution of the universe, and bubble collisions were relevant to what happened at that stage. Anyway, that's part of the motivation, but I don't know really very much about it, so I'm going to stop talking about that now and talk about a 1+1 dimensional version of what I was discussing before, where you have two true vacuum bubbles, and the walls of the true vacuum bubbles are accelerating outward, and the walls of the two different bubbles meet. So here are the two walls rushing towards each other in a 1+1 dimensional setting. And in this false vacuum, in the false vacuum in the middle, the field has a negative expectation value. And in the true vacuum on the outside, it has a positive expectation value. And as the walls rush towards each other, the false vacuum is swallowed up, and eventually they collide and things happen. So we want to characterize these events. So can we compute the dynamics of such collisions? So of course, we'd love to be able to do it in a strongly interacting QFT like the standard model, but naturally that's way too hard to do. So, you might think about a simplified QFT, an interacting QFT like phi-4 theory, which you can treat in 1+1 dimensions. Now you can do some perturbative calculations at weak coupling at least, but you can no longer do this at strong coupling. We'd like a method that works at strong coupling too. Now you also, you can treat strong coupling if, for example, you put the QFT on a lattice. If you discretize it in space, for example, and use a Hamiltonian evolution to simulate the dynamics. And you can do this using tensor network methods like the matrix product state methods that we use. You could also treat lattice phi-4 theory with those. The disadvantage of lattice phi-4 theory in particular is that the local degrees of freedom are bosonic, and there's this, so you have to truncate the local Hilbert space in order to practically do computations. So that's an extra step that you have to take, an extra approximation. So to avoid that, we do really the simplest thing we could imagine, and we take a spin chain. And rather than aiming to do some well-known QFT from like particle physics, we target an emergent QFT near a critical point of the spin chain and decide to look at its dynamics instead. So this could be a chain of qubits, might be the transverse field Ising model. We can do the tensor network simulation, no truncation is needed. And again, we can access continuum physics of some massive QFT if we tune close to some critical point. And the other thing about spin chains is that they're sufficiently simple systems that one can imagine using a near-term intermediate scale quantum device to do such simulations as well, if you can initialize the correct state. And there's some other work by John, Junyu, and Barak, who they've looked at how you might efficiently prepare such states using classical matrix product state related methods in order to program them into your quantum computer, into your quantum device to set up a dynamical simulation. Anyway, that's part of our motivation. So we're going to look at the spin chain setting. And in the spin chain, of course, you can just think of it as a discretized version of the picture I showed you before, where now in the false vacuum, the spins are down, say, and in the true vacuum, the spins are up. And there's some sort of domain wall between the down and up region. And because this is a false vacuum and there's some symmetry breaking field, such domain walls accelerate into the false vacuum, and eventually, if there are two of them like this, they'll collide. And when they collide, new quasiparticles of the system may be produced. So our project is to first understand how to construct good false vacuum bubble states and simulate their collapse, the collisions of these walls in real time using, we were going to use infinite matrix product state methods to do that. We want to try to characterize the emergent continuum physics near to a critical point of the spin chain. So we want to avoid lattice effects, and we take a stab at avoiding the most obvious ones. And we want to understand the computational requirements for such simulations as, for example, as you increase the energy and get more and more particles produced. So how far can MPS go? And, again, part of the motivation for looking at that is to understand where you might get a benefit from doing the simulation on a quantum device. So it's a preview of the results. We can indeed create stable bubble wall wave packets. Now that's important because we don't want anything to happen to the bubble walls aside from acceleration until they collide in our simulations, because we really want to focus on the collision events. We observe that in these collisions, we see elasticity in the transverse field Ising model with a small longitudinal field, which might be considered somewhat surprising just because technically the model is not integrable because of the small longitudinal field, but the field is small, so maybe you would expect it to be close to integrable. And indeed, we see only elastic collisions of these walls up to numerical precision. And by changing the model slightly, adding another term, it's a term that maps to kind of a TT bar term in the CFT and takes you ultimately to a tricritical Ising point. By adding this term, we can get to situations where we have strong inelastic collisions and we can see particle production. And we observed that the entanglement produced in these collisions scales with the energy, as you might expect. There are more possible outcomes as energy increases, and we see some scaling of the entanglement entropy with the energy. And we also observed that for this type of simulation, we need to go to reasonably large system sizes. Our simulations are done on roughly 1,000 sites in order to make the wave packets big enough so that they don't spread out too much during our simulations. Okay, so let me, okay, I thought I'd skipped a slide there. So let me go on to discuss some of the methods, unless there are any questions at this point. Okay. So for this all to work, oh, sorry, go on.
Sorry, yeah. You said that you are using IMPS, but you mentioned also the lattice, number of lattice sites. To me, that sounds contradicting to each other.
Good point. Yes. So we do use infinite matrix product states, but what we do is we define a window in the infinite, on this infinite system in which dynamics are allowed to be non-trivial. So it's, some people call it infinite boundary conditions.
I see.
So we have this window in the middle of n sites. You can grow the window during the simulation if you want to make it bigger as the dynamics spread, but we didn't choose to do that for our simulations.
I see. Thank you.
Okay. So to do all this, we'll need representations of the following states. We need to understand the true and the false vacua of these spin chain models, and we need states representing the bubble walls, and of course, ultimately the entire bubble. Now, this is an interacting system, and it's a quantum system with quantum fluctuations. So how do we capture these states given that they do have quantum fluctuations? That's, by the way, that's why I put these spin up and spin down diagrams in inverted commas, because that's, they're only almost that. They have fluctuations on top of them. So how do we capture those? Well, we're going to use matrix product states. And in case anybody here doesn't know what that means, I'm going to briefly explain how this works. So here's a quantum system. It has 3 sites, 3 bodies, 3 qubits, for example, or 3 spins. And here's a general state for that quantum system. So we sum over basis elements for each spin, I, j, k, and there's some wave function psi I, j, k for this system, discrete number of degrees of freedom. Now we can write psi I, j, k as, well, it is a tensor, right? It has multiple indices, so we can think of it as a tensor. And there's a diagrammatic notation for tensors. And this is the notation. So we have psi ijk equal to this blob here, where we've just added a leg to the blob for each index, and we can label them ijk like this. So this is the diagrammatic notation that we'll be using. Now, a matrix product state is a way of decomposing this blob into multiple blobs, one for each body in the system, one for each qubit or lattice site. So a matrix product state looks like this, where now we have 3 blobs, and there are extra legs connecting the blobs. Now these extra legs mean that we have a 2-index tensor on the left, a 3-index tensor in the middle, and a 2-index tensor on the right. And the extra legs are contracted over, summed over, and they have some dimension which we call the bond dimension, and we can call these legs the bonds, if you like. So you can represent any state, any wave function psi ijk in this form, as long as you make these bond dimensions sufficiently large. So we'll often just use this unadorned notation to represent a matrix product state. These are the bonds, and often the dimension is denoted chi in the literature. These legs represent the spins or the lattice sites. And operations on matrix product states computationally typically scale as chi to the 3, or chi cubed, which makes them efficient to work with as long as chi isn't super large. Now, what determines the size of chi? Well, it has a relation to the amount of entanglement in the state. So the von Neumann entropy for a cut, dividing the system into a left part and a right part, is upper bounded by log of the bond dimension chi across that cut. Okay. So if your system has a lot of entanglement, then chi might have to grow too large for you to be able to do the computations. And if chi in our dynamical simulations, if the entanglement grows too large, then chi will have to grow to meet it. And at some point, our computer won't be able to keep up anymore. So the amount of entanglement in the state is a very important figure of merit for the feasibility of these computations. And you can
in practice currently, how large can you take this bond dimension in state-of-the-art computations?
Well, it depends to some extent what you're doing. So DMRG computations in which you just try to find the ground state can go to, say, bond dimension 1,000 fairly straightforwardly. Dynamical simulations are, if you want to simulate for a decent amount of time, typically work at lower bond dimensions. Ours go up to 128. We could have probably done more by making things slightly more efficient, but dynamical simulations are harder to do because you need to do lots and lots of steps. Okay, so let me continue. Oh, by the way, sometimes you see quotes of bond dimensions in the tens of thousands. That's usually because you're exploiting some symmetry of the system. If you exploit a symmetry, then you can have an effective bond dimension, which is very large, but you only need to store relatively smaller tensors because of the symmetry, which gives you a sort of a block sparse structure. Anyway, that's just an aside. So for the vacua in our simulations, we use infinite matrix product states, as I mentioned. So the dressed version of this all spin up state, which might be the true vacuum of the spin chain, is represented as some infinitely long matrix product state like this. And we find the parameters, and it's translation invariant, so all of these tensors are the same. We find the parameters of these tensors via an energy minimization procedure. It's a variational method. And to find the false vacuum state, what we do is because this is obviously not the lowest energy state of the system, we've got a symmetry breaking. In fact, in an infinite system, the energy of the false vacuum is infinitely larger than the true vacuum. To find this state, what we do is we flip all the spins, starting from the true vacuum MPS, we flip all the spins. That gives us a state in the false vacuum sector, if you like. And then what we do is we further cool this state a little by minimizing the energy up to some numerical precision. And we find that if the strength of the symmetry breaking field is not too large, we effectively get an eigenstate in the false vacuum sector using this method. So we find a stationary state, and we call that our false vacuum state. Now you can actually show, there's a note in our paper, you can show that you can arrive at a false vacuum almost eigenstate using this method. You can do a perturbative calculation and work out that if you, for example, start with the flipped true vacuum and do some amount of imaginary time evolution, you'll need to do a very large amount to get to the true vacuum, because generically there's some overlap with the true vacuum after you flip the spins. But if you only do a moderate amount of imaginary time evolution, you can get to something which is almost, again, almost an eigenstate in the false vacuum sector. Oh, what happened there? Sorry. If you're interested in details of that, I can say some more, but perhaps later. Anyway, but we have this cooling procedure, and we then have, as a result, this tensor, the blue tensor for the true vacuum, and the red tensor representing the false vacuum. And if we build infinite chains from them, we get the true and the false vacuum states, respectively. So we've got those. Now we want to have states for the kinks, or the bubble walls, if you like. So before I describe how we do this, I want to discuss briefly another way of getting false vacuum bubble states, and that is to take the true vacuum, say the MPS representation of the true vacuum, and just flip all the spins in some subregion of the lattice. So flip all the spins, say between sites XL and sites XR, and that kind of looks like a false vacuum bubble, right? With the important difference, of course, that the false vacuum is then not this false vacuum eigenstate, but maybe only close to it. But nevertheless, if you ignore that, it's some sort of false vacuum bubble. Why not just do this? Well, the main reason is that these domain walls that you've created are very UV objects. They're as spatially localized as you can have. And hence they'll have quite high energy, and they'll typically be unstable. And they will decay immediately in your simulation into lots of different quasiparticles of the system, both topological quasiparticles, kinks, and non-topological particles. Now you can mitigate this somewhat by smoothing out these walls by smearing them. So take some, say, a wave packet function f, and smear out these walls to make them spatially delocalized and give them some finite momentum. That reduces the energy, but nevertheless, these kinks are still not topological quasiparticles of the system, and they will typically still decay into other true quasiparticles of the system. And we don't want that. We just want stable bubble walls that will accelerate towards each other and collide. So doing this, using a string to create your bubble, results in unstable walls with relatively high energy. Instead of doing this, we construct approximately kink quasiparticles of the system, so topological quasiparticles of the system, by building matrix product states out of the true vacuum tensors and the false vacuum tensors, and including some tensor in the middle that parameterizes the domain wall-like kink between the two topological sectors. Sectors is not quite right, between the true and the false vacuum. Now, this is not a new idea, by the way, creating these kind of quasiparticle states. But anyway, yes, before I
But
discuss.
this tensor is
Oh, sorry.
really just on one side. That's enough to just insert this tensor on one side.
For our purposes, yes, but you can you have a choice there, right? So you could insert a tensor on a bond, or you could insert a tensor on 2 sites, or 3 sites, or 4 sites if you needed to. You might want to do that in order to get a better approximation to the quasiparticle excitation.
But why do you have this freedom? Suppose that you go to the limit when the symmetry breaking goes to 0. In this limit, your system has some kink states, and those kink states, they have a very precise profile, which is not up to you to decide. I would imagine that your states should have very similar profile.
Good.
If your
so
breaking is small.
Okay, so let me explain what these states look like. So maybe this will help. So this green tensor does not represent an excitation localized to a single site. Because of the correlations in the state, it actually has access to sites, say, up to a correlation length away from the location of the tensor. So it represents some excitation which lives on a collection of sites. It's a quasi-local excitation that lives on a collection of sites centered around this tensor.
Okay.
Whether one tensor is enough or not, that somewhat depends on the amount of correlations present in the vacua. So for example, you could try doing this for the AKLT model, which is an exact matrix product state form. If you weren't, you don't have to do topological excitations. I should stress that you can also use the same ansatz to find non-topological excitations by just putting the true vacuum on both sides of this green tensor. If you do this for the AKLT model, where the vacuum has a bond dimension of exactly 2, you find one tensor is not enough to accurately represent the excitations, and this is because there just aren't enough correlations in the vacua to get a good accuracy. So you have to use a larger block of sites, a larger tensor in that case. Now for our case, one site appeared to be enough. You have a choice there. So you have it. Sorry, go on.
I have a question. So this green tensor, is it determined in terms of the blue and the red, or is it something completely independent you put in?
Right, I haven't told you how to figure out what tensor to put there yet. So at the moment, there's a big question mark there, and that's because I haven't explained this part yet. So if you put just something random in there, you'll get some sort of garbage in the middle and some high energy type excitation in between the true and the false vacua. So how do you find the appropriate green tensor to put there? So we can use an optimization procedure to do that. So what we do is we take the momentum eigenstate built from a superposition of these localized kink type states where the green tensor is superposed across all sites of the system, and we can give this some momentum p. So it's a momentum eigenstate with momentum p. And what you can then do is you can form an effective Hamiltonian for the green tensor. And because now this is easier to explain if there's no explicit symmetry breaking and you can have low energy topological excitations in your system, low energy kinks. In that case, this is old news. You can do this optimization. You can form the effective Hamiltonian for the green tensors, and you can find kink quasiparticles of the system. So you could just take the Ising chain and go to the symmetry broken phase. You can find such kink quasiparticles. And you not only get the green tensor, but you also get you can vary this momentum p, and you get an energy for these eigenstates of the Hamiltonian, and you can get a dispersion relation for the topological quasiparticles. Now, for our case, the true and the false vacua, of course, have different energy densities, and these kink type states are not really eigenstates of the Hamiltonian. In fact, they're far from it. So in order to find these green tensors in that case, what we do is we build an effective Hamiltonian where we effectively just subtract off the position-dependent energy of the kink. So the energy of the kink depends on the position, it just depends on the amount of false vacuum that's present. So the more false vacuum that's present, the larger the energy. And if we can subtract off that difference, we can build an effective Hamiltonian where the kinks are again eigenstates, or these momentum eigenstates are also Hamiltonian eigenstates, more precisely. And then we get then we can find the kink quasiparticles of that effective Hamiltonian, and those turn out to be good stable kink excitations for the true Hamiltonian of the system, despite them not being eigenstates of the true Hamiltonian. Okay, so
sorry,
yes.
Naive question. So this formula for psi you wrote depends on what you picked for the green site originally, right? And I'm just trying to understand. So you write that as a function of that tensor and P.
That's right. That's right.
And then you compute this energy as a function of momentum, but it still depends on what you put in the green site.
That's right. So what you do is for each chosen P, you can get an effective Hamiltonian within that P sector, within that momentum sector. You get an effective Hamiltonian where the states are just determined by the green tensor, right?
And then you're taking the ground state of that effective Hamiltonian, or what state?
Well, we can take okay, good. So yes, we can actually find multiple eigenstates of that effective Hamiltonian. So we're not limited to the ground state. You can run it through some sort of sparse eigenvector solver, and you get a series of eigenstates. So the lowest one will represent the lowest energy kink excitation, and then the next highest one will represent in most of the case, okay. So I should clarify that this ansatz for excitations is only good for excitations that really are quasiparticles. So if you think of your spectrum as having some lowest energy quasiparticle branch like this with some mass m, and then at mass 2m, of course, scattering states begin and the spectrum becomes continuous. This ansatz is good for representing isolated branches within the spectrum. So if there are two isolated branches before the continuum begins, then you can represent both of those by just finding the two lowest energy eigenstates of the effective Hamiltonian.
Okay, thanks. So you have like multiple types of kinks, sort of like.
Yes, you can, and indeed in one of the models, in the modified Ising model that we treat, we have two types of kinks that are interesting for us.
Okay, thank you.
Okay, so once we have these localized, once we have these green tensors, we can again localize them. And rather than building momentum eigenstates, we can put some wave packet function f in front of these states and build a localized wave packet. So we take, say, a Gaussian f, and that gives us some state which is localized both in momentum and space. And depending on the width of the Gaussian, it's either going to be more or less localized. So if we have a narrow packet in space, of course, that has some fairly broad support in momentum space, and hence a relatively large energy. If we're targeting momentum 0 and we have a broad packet, a narrow spatial packet, it has a broad momentum support and quite a large energy. And if we make the spatial packet broader, of course, that focuses in momentum space by the Fourier transform, and we get a relatively low energy wave packet. And we're going to want to have relatively low energy wave packets, relatively focused wave packets in momentum space, because that is going to help us minimize the spread, the spatial spread of the wave packets during the simulation. We want things to remain localized, partly so that we can characterize what happens in these simulations, and stuff just doesn't just mix together and become difficult to distinguish. So we're going to have spatially broad wave packets. Now, that means we've found a way to get the true and the false vacua. We've found a way to define localized kink states by building wave packets from these green tensor states. And then all we have to do is build a bubble packet by combining a kink and an anti-kink. So this is what that looks like. We have a green tensor for the kink, a different green tensor in general for the anti-kink. We have the true vacuum tensors on the outside and false vacuum tensors in the middle, and that's our initial state for our simulation. At least it is after we've smeared these out into wave packets. So we have a wave packet function F for the kink and a wave packet function G for the anti-kink. Now, I should say it's important that the kink and the anti-kink tensors are not too close together, because we found these green tensors in isolation, assuming there are no interaction effects. So we have to keep the kink and the anti-kink far enough apart in this initial state so that we can neglect interaction effects between the kink and the anti-kink. In other words, we have essentially asymptotic states for the kink and the anti-kink prior to the collision. So for our simulations, we choose the kink and the anti-kink quasiparticles of this effective Hamiltonian. We choose them to be the kink and the anti-kink of lowest energy, but we could have chosen them again, since there is a higher energy kink, to be higher energy, but we chose the lowest energy ones for our simulations. And then what we do is we take the state and we time evolve it, and the method we use is a variation on the time-dependent variational principle, where we add some methods to expand the bond dimension as needed as the entanglement grows. And again, this is a simulation that takes place in a window of the infinite chain, and we define some number of sites for this window where the dynamics are allowed to be non-trivial. Now, as the state evolves, we can actually characterize the particle content. So the way we do this is we take overlaps with quasi-particle states of the form we use to construct the initial state. So for example, this kappa bar state is just a kink-antikink state, and it's the same type that we use to construct the initial state for the simulation. And if we take overlaps of the state as it evolves with these kink-antikink states, we can use the overlap with these states to understand how much of the wave function is still in the kink-antikink sector as time evolves. And we can do this for other types of excitation too. We can do it, for example, for a single non-topological excitation on top of the true vacuum. So blue tensors all around except for some green tensor in the middle. This is some non-topological excitation. Again, we find green tensors to represent the quasiparticles of the system in this sector. And then we take overlaps with those states. So that's a single meson, if you like. And we can also make meson pair states and take overlaps with those. Now you have to take some care to make sure these effective sectors built from these states are actually orthogonal to each other. So for example, in the two particle states, you need to make sure that you need to make sure you take into account that there are interactions between these particles in general. So we just simply discount, we simply remove from our basis all the states where the A and the B tensor are too close together, such that interactions would occur. So in that sense, we restrict our basis to asymptotic states of these particles where they're not allowed to interact. They're just too far apart.
Question?
Yes.
So the way you determine the green tensors in the first line versus second and third line are different, right? I mean, they stand for different tensors.
They're different tensors, that's right.
But
it's not
you
completely clear
effectively, right, but you use the same method in that you are computing the effective Hamiltonian for them and basically find the energy against states.
That's exactly right, yeah. So and I should stress again, this is not a new thing. This is these are methods that were developed years ago. 97, I think, is the first instance where people looked at this type of state. I think Romer and Ostland, and yeah, they looked at it periodic boundary conditions. I think the non-topological version of this, and they called them block states.
I see. And for the second and third state, let's imagine that they carry some momentum. I would imagine you actually, in practice, took some momentum against state.
Ah, yes. Well, so to compute the particle content, we have we can indeed just take overlaps with momentum eigenstates. Yes, we can build momentum superpositions from these and take the overlap to get the amount of the state in that particular momentum sector. And we do indeed want to do this because actually something I haven't mentioned is that these tensors have a momentum dependence, as you might expect, since you solve this momentum dependent effective Hamiltonian for the green tensors, there is some momentum dependence in general. Right. So to detect the particle content properly, you should actually project into different momentum sectors where you use the appropriately tuned green tensor for that momentum.
I see. And once you take the inner product, you integrate over momentum to say like whether your initial state has some portion of this sector versus the other sector.
Yeah, we effectively integrate over momentum. We do some discrete approximation to the integral over momentum.
I see. I see. Thank you.
Okay. So that's as much as I'm going to say about the methods for now. Let me talk briefly about the model that we're using here. So it's a modified Ising chain with both Ising and tricritical Ising criticality. And it was studied recently, relatively recently, by Edward O'Brien and Paul Fendley and Hosho Katsura and his collaborator. And it's interesting because it has, because you can think of the term different to the regular transverse field Ising model as being a TT bar type term in terms of the CFT. Anyway, but what do we actually want from our model? Well, we can take any spin chain. You know, we're not too picky at this point. We want some version of a false vacuum bubble. So we need at least a false vacuum, and we'd ideally like these false vacuum bubble walls to collide inelastically, of course, so that we can see some particle production.
Can I ask a question?
Yes.
Question. So maybe I'm thinking too naively, but aren't there also spin chain models where you have not false vacuum, but at least in the continuum, true vacua, that you have several vacua, like this RSOS models, relativistic solid on solid, I heard once. So you have various vacua, and yes, the kinks that interpolate within different vacua, but I thought they were real vacua, not false vacua.
Right. Yes, I mean, sorry, go on. Was there another question?
I was just wondering if there will be two complications at once. One, the fact that this vacua is not a true vacua, and the other one, particle production. So you could isolate one of these effects by looking at theories where the vacuum is a true vacuum, and you would still focus on particle production.
Right. Yeah, so there's no reason why we couldn't do this for without the symmetry breaking field and look at particle production of kinks between true vacua, or collisions of kinks between true vacua rather. We were particularly interested in the false vacuum setting, but there's no reason you can't apply the same techniques to study collisions of topological excitations between different true vacua, or indeed collisions of non-topological excitations. Okay. So the model we chose indeed is basically the transverse field Ising model, ZZ coupling, transverse field X with parameter G, and longitudinal field Z with parameter H, plus an extra term, again looked at by these authors recently, a three-body term ZZX and XZZ. And if you turn on this lambda coefficient and you start from the critical point of the Ising model, you'll eventually push to a tricritical point. So the model remains Ising critical for some finite value of lambda until you get tricriticality, and after that, the system gaps out again. Now this is good because this model is good because if G, the transverse field strength, is less than 1, there's spontaneous symmetry breaking. And if we turn on this H field, of course, we can explicitly break that symmetry and go from having multiple true vacua to having one true vacuum and one false vacuum. So this term is key in that. And at least for sufficiently large lambda, we're far from integrability, at least on the lattice. And so we can expect to have some interesting dynamics and some particle production. So here's a phase diagram, just to clarify. So on the bottom, we have the Ising chain. So on the left, this is without the symmetry breaking field, h equal to 0. We have the Ising chain, which is a theory of free kinks, if you like. And then there's the critical point at g equal to 1. And if you turn on lambda, you get this Ising critical line and a tricritical point. And for g less than 1, you have interacting kinks as soon as you've turned on this lambda term. Now, actually, there's also some line of trivial vacua going roughly along here, but I'm not going to talk about that for trivial in the sense of product state. I'm not going to talk about that for the purposes of this talk, because the points that we'll consider are away from that line. This point down here, this point over here, this point over here. So for a non-zero symmetry breaking field H, we'll look at a point of the Ising model to see what happens there. It's technically not integrable, but it's close to being integral because H is small. And we have another point closer to the tricritical point and another point even closer to the tricritical point here. So here are some results, unless there are any questions about the model first. Okay. So first, I want to convince you that the kinks that we construct using this this ansatz are actually what we wanted them to be, in the sense that they're stable, and the only thing that happens to them under the evolution by the Hamiltonian is acceleration until they collide with something. So this is the spin profile of a kink, spin expectation values. The false vacuum is on the right and the true vacuum is on the left. And at time 0, the kink is in this position. This is what the kink looks like. It's again a wave packet formed from these green tensor states. And as time evolves, the kink accelerates. These different curves are at constant time intervals. And it accelerates, of course, toward the false vacuum, because that's the energetically favorable thing for it to do. Now, if you look at what happens over longer times, I'm going to switch to a top-down view, if you like, where blue is now the true vacuum and red is the false vacuum, and the kink is white in the middle. So if you start your kink, the y-axis is time and the x-axis is position. If you start your kink at time 0 at some position, at momentum 0, then as in the previous plot, it accelerates toward the false vacuum. But ultimately, it reaches some maximum velocity, and after that, it eventually decelerates, goes to stops, and turns around and goes back the other way. Now, this might seem a little strange, but it's expected from it's an expected effect of the lattice. Let me put it that way. But what can we see from this plot? We can see that the kink, apart from this strange behavior, is stable. It doesn't decay into other particles, at least up to good approximation. But we do have these strange oscillatory behavior over long times. So let me first explain what's going on there. So I've said this is a lattice effect, and it's something that's called a Bloch oscillation. So it's related to the dispersion relation of these kink quasiparticles. So even for this symmetry broken case, we can take the effective Hamiltonian I mentioned, where we subtract out the energy difference as a function of position, and we can get some kind of dispersion relation for these kinks. Now the energy is relative, so I've just started it at 0 here. But there's some dispersion relation, and this being a lattice system, the momentum is bounded. It runs, in our case, between -pi and pi. So the dispersion relation for these kinks has to be periodic. So it starts off looking kind of like some relativistic dispersion relation, getting almost linear over here, but then it curves back around and it's periodic. This is the value pi. It'll loop back around and go back down to 0 eventually as we go around the unit circle. So why does this explain the Bloch oscillation behavior? Well, the velocity of the wave packet for a quasiparticle at some momentum p is just the derivative of this dispersion relation. So the derivative of the dispersion relation reaches some maximum at this almost linear part, and then it begins to decrease again. So there is some maximum velocity around here at a particular momentum. And so if the momentum increases and increases, what you'll see is the velocity increases up until this point. The momentum will continue to increase, but the velocity will decrease. And eventually it'll go to zero as the derivative of this dispersion relation goes to zero. And that's indeed what we saw in the previous plot. So we can match this behavior up to our simulation. In the simulation, we can track the location of the kink by just looking at where the spin expectation value crosses zero. And we can compare it to this dispersion relate to the derivative of this dispersion relation, and we see that there's a nice matchup. Now, how do we get the momentum from our simulation? We have to somehow find out what the momentum is as a function of time. Well, we just what we effectively do is we project into our quasi-particle basis of single kinks, and we take a Fourier transform to find the momentum. And in fact, it's worth noting perhaps that the momentum of the kink it simply increases linearly with time. Or if you like, since it's a periodic value, the momentum, it processes at a constant velocity around the unit circle. So you can think of this p-axis as equivalently as time. There's just some factor.
Sorry, can I ask something? So
Yes.
did you change a little bit the construction of the kink between the first time you introduced and now? Namely, I'm a bit confused by the following. So before, I thought you were considering wave packets at fixed p, right? And now it looks to me like you don't fix p. You let it go. You start to move.
P changes during the simulation. So this is during the dynamical simulation.
Why does P change? Sorry. I thought you prepare a state with a given P, right? And then
yeah, we prepare our initial state with P equal to zero. So we have a stationary localized kink, but then because we have a symmetry breaking, the kink wants to accelerate in order to swallow up the false vacuum. So the momentum changes because this is not these kinks may be momentum eigenstates, but they're not Hamiltonian eigenstates of the system.
Okay. So if it was so that's an example. If it was really an honest vacuum, of course you would not have this.
Right. If you had two different true vacua, then you wouldn't see acceleration, and the momentum expectation value would stay the same. Right. But you don't have momentum conservation. You can think of it in this case. You could think of it in the following way. This state has an infinite amount of false vacuum and an infinite amount of true vacuum. So its energy with respect to the vacuum is infinite. But you could think of it as one side of a very large false vacuum bubble. So there's a very large blob of red. And in that case, there'll be another wall on the other side. And both of these walls will do the same thing. They'll both accelerate inwards towards the true vacuum. And they'll both undergo these Bloch oscillations ultimately, as long as the bubble is large enough. Until they delocalize. Of course, if the bubble is small enough, the two walls will meet each other before they're able to complete their Bloch oscillations and collide. And that's the situation we actually want to look at. And in fact, we want to look at the situation where that happens before you start to see these Bloch oscillations, before the velocity reaches its maximum, because what we want to avoid these lattice Bloch oscillation effects, and we want to try to get at the dynamics of the relativistic field theory that emerges near the critical point. So we want to avoid this sort of oscillation. So we want to start the other kink maybe say here at around site 100 so that they collide before the maximum velocity is reached. Okay, so let's look at the dynamics of some bubbles. This is what you see. Oh, sorry. This is what you see near, kind of near the tri-critical point in this extended Ising model.
But sorry, let me just ask a question. So,
sure.
Here I should really think of this as like endpoints of a meson, right? So these two particles that you would scatter, and the red is like a string that stretches between the two, right?
Yes, you could think of it just as well as an extended mesonic excitation where you have two confined quasiparticles. Yeah.
But then even when they are far apart, it's not true that the potential between them is zero and then there is an interaction region and then it's zero again in the future, right? In the infinite past, they start immediately when they start moving, feeling a linear force between the two, right? They start immediately being pulled towards each other.
Right.
So
but
in that sense, it's a bit it's a bit different from a standard scattering experiment, right? Where we first separate them a lot, they don't feel each other.
That's right.
And later they will feel each other.
It would be as if you'd taken two quarks and pulled them apart a long way and then just let them bounce back together.
Right. So it's a bit different from a scattering. If it was true vacua, or if they were mesons, then it would be closer to a scattering experiment.
Yeah, I mean, I think it's still very close to a scattering experiment because indeed the force felt by these mesons does not depend on the distance between them at all prior to interaction. So, you know, in the previous plot where I had just one kink, I had an infinite amount of false vacuum. And that behavior of that single kink is indistinguishable from just a kink that is separated by a long way from the antikink. So it's not really like it's not really an interaction effect. I think it's really just due to the false vacuum in between. I mean, you know, you have to have another kink if the energy is to be finite. So you can think of it as interaction if you like, but it doesn't have some range associated with it.
No, I'm not sure I agree. Why not? I mean, it does have units, right? Because there is a string tension, right?
Right.
So,
well, okay. So
the force is constant, the potential grows linearly, right? So the toy model in quantum mechanics, it would be a linearly growing potential instead of a potential that goes to zero, right?
Yes.
So if the potential goes to zero, we have plane waves. If the potential grows linearly, we get some ID functions at infinity. It's a bit different, right?
Yeah. So I think string tension is the right way to think about it. So there's some string, and as you pull these things apart, you're putting more and more energy into this string, but the particles at the end of the string don't really see each other until they get sufficiently close. They can have their own interactions independent of the string, but they don't have those until they get quite close to each other.
Thank you.
Okay, so here are two different strengths of the longitudinal field. So what I've done is I've created essentially the same initial bubble state in both cases with the same initial separation of the kink and the anti-kink, and I've used the two different field strengths to change the energy. So the larger the field, the more energy is in the false vacuum, and the faster these kinks will accelerate, or the kink-antikink pair will accelerate. So on the left, the field is lower, and actually the energy of this state with respect to the mass gap of the system is 1.8. So that's 1.8 times the mass gap, which means there's not enough energy to create a pair of particles. So it's below threshold, whereas the energy on the right is above twice the mass gap, and there is therefore enough energy to create a pair of the lowest energy quasiparticles of the system. And as you can see from this lower plot, which shows the energy density on a logarithmic scale, indeed something flies out ballistically from this first collision between the kink and the anti-kink. And it looks a lot like a pair of non-confined particles, which is what we'd expect from the energy. So indeed, we can see that by setting the energy above threshold, we get some inelastic scattering happening, and below threshold, we apparently do not.
I'm sorry, Ash, but after the first collision, if we have these two pair of particles,
yes,
this energy, how did you compute the energy? It's taken into account the how much energy they can extract from the false vacuum.
Right. So indeed. So this is computed very simply. So we create this initial state, and we just measure the energy using the Hamiltonian. This is the so this includes the energy contained in the false vacuum, as well as the whatever energy the kink and the anti-kink themselves have.
I'm just worried because after the first collision, you subtract 2 units from this energy, right? So you're left only with 174. But this doesn't look like that's what's happening, because the kinks, they still separate to almost the same separation as they, and on the next collision, they again produce something. So it looks like they keep extracting energy. It looks like it's a perpetuum mobile.
Right. Well, okay, so you could, okay, so what happens, I think a good characterization of what happens is as follows. So at the first collision, there's a scattering event, and there's some probability of just a bubble emerging again, the same sort of kink-antikink bubble emerging again from this collision. And there's some probability of the bubble being converted completely into a pair of low energy mesons that then fly away. So you could think of these two outcomes as different branches of the wave function. So on the bubble branch, where you just stay in the bubble state, within that branch, the energy is the same as it was before. And in the other branch where you have the mesons, all of the energy has been converted into the kinetic energy of those mesons and their mass, of course. Okay. But you do, so one thing you do see, the bubble sort of does change shape as time goes on. Partly this is a delocalization effect, because these wave packets do spread at some rate in time, because they're not, because this is a quantum system with fluctuations, and so any localized wave packet will slowly spread. So you're seeing those effects too. Okay, now before I go on, I want to show you a brief comparison of this kind of simulation that I just showed you and what happens if you create your false vacuum bubbles using a string. Which is what I mentioned briefly, an alternative construction. So on the left, this is a simulation where you just, you don't do any spatial smearing, you just hit the vacuum with a string of some width, and you create a bubble and you simulate. In the middle, we have spatial smearing on top of that string, and on the right, we have our construction where we have the full quasiparticle wave packets. So I should say at first, there are errors that occur in the simulation in column A. I use the same simulation parameters, the same numerical parameters as I did in the other simulations, and it just wasn't enough to successfully simulate the dynamics on the left past time 150 roughly. So this non-causal kind of weird line is where the simulation breaks down on the left. So it's kind of hard to do these simulations compared to the other simulation. This is because this is a relatively high energy state, very localized, and there's lots of particles being produced and lots of stuff happening. Whereas in the simulation on the right, we just have these kinks, nothing really happens to them until they collide. Now in the middle, where we've smeared the kinks, it's much more like our simulation on the right, but you can still see, if you look at the energy density, there are some quasiparticles being produced at the initial bubble walls, so they're not stable. And if we did the simulation, we'd be simulating the dynamics of these extra unwanted particles as well. So by using this green tensor construction where we optimize for quasiparticles, we can eliminate these effects too and just get a nice clean simulation where the only particles produced to good approximation are at these collisions. And this is good because also it's easier to do. The more quasiparticles present, the more entanglement is produced and the harder the MPS simulation gets.
Actually, when you say particles are produced, is it 2-to-2 scattering or 2-to-4 scattering or something? Before it looked like it was 2-to-2. It was just 2 kinks to 2 particles.
2 kinks to 2 particles, yeah. So when I say particles are produced, in the simulation I showed you previously, that's what happened. It was 2-to-2. Now in the left and the middle columns here, we get all sorts of stuff happening at the initial bubble walls. Presumably there are meson pairs being produced, but presumably other stuff is happening too. I don't have a full characterization. I didn't try to fully characterize the quasiparticle content of those states. Basically because that wasn't the event we were interested in. But if you create these sharp bubble walls by just flipping spins, then you're bound to get some mixture of different quasiparticles. And I think that's what we're seeing here. I don't know if there's pair production happening here, or if these are just particles that exist in the flipped spin state. Okay. Something new on the bottom. This is the entanglement entropy across a cut that I talked about, which is important for the MPS simulation. And you can see the entanglement entropy also shows you where the particles are, essentially. But I'll get more into entanglement later.
But actually, Ash, how much time do you still need?
Let's see, not much. I see that, yeah, I'm basically at time now. So there's not much left to show you. The main thing I want to show you is what happens in the Ising model. So in the Ising model, we look at these parameters here, quite fairly close to the critical point versus the tricritical Ising model. Both of these simulations are well above the threshold for pair production in theory, but in the Ising model, which is only slightly non-integrable, we don't see pair production at all. We just see the kink-antikink bubble re-emerging from each collision. Now, what we did to try to confirm that this was indeed an elastic scattering event in the Ising case was we took these overlaps with these quasiparticle states in different sectors. In fact, we only looked at the overlap with the kink-antikink sector. You know, if this simulation remains in the kink-antikink sector, then we can be pretty sure it's an elastic scattering event. And indeed, that's what we see. So this is the probability of the state not being in the kink-antikink subspace as a function of time. The blue curve is the Ising model. So in the initial state, we are in, to good precision, we are in the kink-antikink subspace. That's how we constructed the state. So we get some small error of around 10 to the minus 5. The kink and the antikink then collide. Well, they're interacting, so we can no longer characterize them as separate kink and antikink states. But after they re-emerge from the collision, we find that indeed they are still in the kink-antikink subspace, and there aren't any other significant pieces of the wave function. And these different curves are different bond dimensions. As we increase the bond dimension, we get better accuracy and therefore a better characterization of this, this overlap. Now, in the tricritical Ising case, we see a different picture. The first collision, again, the overlap with kink-antikink goes down. But then afterwards, it stays down because we produced some mesons which are in a different sector. And so we have some like persistent portion of the wave function not in the kink-antikink subspace. Mm-hmm. So from this, we take the lesson that Ising, at least to the precision we were able to get to, seems to be elastic. And this actually ties in quite nicely with some recent work showing that there are like non-thermalizing meson-like states in the Ising model with transverse and small longitudinal field. They use different methods. There's one that tries to find like approximate effective symmetry operators in this model. But anyway, that's other people's work. But it was nice. We were confused when we first saw this, and then we found that there was this other work, and that kind of helped us feel better about this being completely elastic, despite technically being non-integrable. And we can also use these quasi-particle basis overlaps to characterize what happens in the inelastic case of the tricritical near the tricritical point. So what we did was we picked a simulation, we picked a particular time after the collision, and we looked at the probability of being in each sector. These are 4 different sectors. There's the original bubble sector of kink-antikink of lowest energy. There's the 2 meson sector. And there's also a sector which we found was relevant where you have a kink of lowest energy and an antikink of higher energy, or vice versa. So you can get a different sort of false vacuum bubble where one of the kinks becomes excited. And we found that there was some amplitude within that state too, within that sector too. We can compute probabilities for these, and it was more difficult to compute them in this latter case because the kink and the antikink just weren't able to get very far apart. They're still confined, and because one of the kinks is heavier, they don't go as far. And so we run up a little bit against this separation issue. But if we were able to decrease the lattice spacing or increase the energy, we could probably characterize that better. So briefly on entanglement. The entanglement, the top plot is the maximum cut entropy, which is the maximum like saturation of the bond dimension, if you like, from the MPS perspective. It's more or less constant before the collision because nothing much is happening except these kinks are moving. At the collision, a bunch of entanglement is produced, as you might expect from the interaction effects. As things move away from the collision, the entanglement sort of plateaus. But if some part of the wave function remains in a confined sector, there's another collision and more entanglement is produced and another collision and so on and so forth. And as things delocalize, these collisions kind of get smeared out in time as well. But we see that if we wanted to simulate for a long time, it gets very difficult as the collisions build up and more entanglement is produced. And another thing we can look at is the entanglement produced in the first collision as a function of the energy. And these plots show that. So I'm going to focus on the black curve here, which shows a point quite close to the tricritical point. As we increase the bubble energy, and in this case, we do that by increasing just the separation between the kink and the antikink. The maximum entanglement produced during the first collision increases and increases. Now, we don't have perfect precision as the energy gets rather high here. We probably need to increase the bond dimension more to finish off this curve. And we can't make the energy arbitrarily high without encountering these block oscillations before the collision occurs. You know, we can't separate the kink and the antikink too far because otherwise they'll start to oscillate before they collide. And the maximum velocity reached is this light colored curve in the background. So we're kind of approaching the maximum velocity as the energy gets high up here. But I think at least this shows that the simulation certainly gets more difficult as we increase the energy. And if we were to move closer to the continuum limit, which would allow us to reach higher relative energies before reaching the maximum velocity, then we'd see this trend continuing and we'd see the entropy continuing to increase. But, you know, obviously one should check that. So with that, here's a summary. We've seen that we can construct these stable kinks that do not decay into other particles until they collide with something. And we've seen inelastic false vacuum claps in this, or bubble wall collisions in this modified Ising chain, and we can characterize the particle content to some extent. We've seen that in order to avoid lattice effects like block oscillations, you might need to get fairly close to the continuum limit, like to the critical point of the spin chain in this case, which means in order to get stable wave packets that don't spread out too much as your simulation proceeds, you might need to make them quite large. So there's a trade-off between system size and the extent to which you see lattice effects. We're continuing to look for, or we'd like to continue to search for models that would allow us to access interesting continuum physics at moderate system sizes, because that would be relevant for whether or not you can get a quantum advantage from some NISQ device. And, you know, there are many places you could go from here. You could increase the energy. You could try to take and see, you know, what kind of particles you could produce as you do that. You could take a continuum limit by getting closer and closer to a critical point. You could look at harder models with, say, higher central charges of their critical points for more interesting dynamics. And of course, you could potentially extend this to higher dimensional systems. And one other thing that will be interesting is looking at how bubbles of true vacuum can begin their life, like tunneling processes or other bubble nucleation processes, which would shed some more light on the dynamics of these vacuum bubbles. So with that, thank you very much for your time. Sorry, I'm slightly over. Well, maybe I'm 10 minutes over. I don't know. Yeah, apologies for that.
Thanks, Ash.
Thank you. Can I ask a question? So, would it be possible to see the formation of a meson, namely starting with two kinks and releasing them and letting it form a stable meson? So right now they are scattered, they scatter back and forth, right? So they would have to somehow lose energy to infinity to be able to stabilize into a meson, right?
Right, yes.
But there should be some experiment like that, right? Like
well,
an electron and a proton approaching and forming an atom, right? They would do it by approaching slowly, radiating photons, right? So if you can simulate that,
yes.
then they can form.
I suppose so. That's an interesting question. Yeah, I haven't really thought about that.
Because maybe that process would be like a physical way of measuring the coupling between kink-kink and meson, right? That normally we see in, say, the S matrix in some residues in some unphysical positions. But it should probably also control this process, I guess.
Right. Right. I mean, in principle, you can also look at like scattering outcomes where you just have a single like stable meson quasiparticle. But I guess, yeah, there's too much energy in the simulations we looked at for that to occur. Because if you have a zero momentum meson, it just doesn't have enough energy if it's below the threshold.
So what would happen in your simulations if you scatter things? If you scatter two kinks where the energy of the two kinks is slightly above the energy of a single meson at rest?
Right, if it was slightly above the energy of a single meson, then it was slightly above the energy of a single meson at rest. I'm not sure right now, actually. I guess I would see, I guess I would kind of expect to see the same sort of thing we're seeing when we're below threshold. I think you would just see the bubble re-emerge and some breathing oscillations continue.
Wouldn't you expect that the breathing oscillations decrease and decrease and decrease because it's going to the stable meson? And at the same time, you keep losing small, like the analog of photons that are radiating to infinity.
No, but the model has a mass gap. There are no photons. That's the problem.
Yeah, I don't see how, I don't think it would, there's no easy way for it to lose energy, right? There are no massless excitations, for example, yeah.
Yes. Okay.
I mean, it looks like you have an amazing machine which can compute S matrices, but I tend to agree with Pedro. This whole focus on false vacuum bubbles. I mean, this sounds cool, but I think it's just a red herring because the connection with, I used to be a phenomenologist and I studied all this false vacuum and standard model and everything, and I think the connection is very far-fetched.
I see.
I don't think you will be able to say anything particularly interesting there because those calculations are not strongly coupled. I mean, people have computed this in the standard model. People know how to compute the lifetime of the false vacuum, and so we know that we live in the false vacuum, but we live in a pretty safe from the life of this of this false vacuum is.
We weren't trying to compute the lifetime. Obviously, we just wanted to see. We wanted to look at the particle production when you have these collisions. That was what we were interested in.
I have maybe a mundane algorithmic question. When you do this time evolution, you're sort of truncating the bond dimension somehow.
Right, kind of, yeah.
I'm not sure you're interested in going to longer times, but I was just wondering if you're using this folding algorithm that Hastings and David Hughes and other people proposed, because that allows you to do like much longer times. And I'm not
right. I'm not certain. I know which algorithm you mean, but is this the one where you set out the tensor network for the entire time evolution and you just contract it in a different way? Or,
yeah, exactly. You have the bra piece, you put the operator, then you have the ket, and you fold sort of the bra and the ket and you fuse the tensors, that basically, there is some entanglement due to free streaming of these quasiparticles that cancels out in that way of doing it.
I see.
So you take into account like this mundane kind of buildup of entanglement due to some free streaming. And okay, maybe, yeah, it depends on what one is interested in, but usually that allows you to go to longer times.
Yeah, I don't know to what extent. I mean, the approximations you make there, because you'll have to do some truncation there as well, are going to look a bit different, and I don't know to what extent.
It just stretches your time window. Like you were going up to time 400, maybe it allows you to go to like 1200 or something. It's like an order 1 improvement.
But is that, how generic is that improvement, I guess would be my question.
Well, I think it's generic if you think the buildup of the entanglement is happening due to some free streaming of quasiparticles, which seems like the case.
Yes. Well,
in your models.
okay. Well, it's quite different to like a quench, because in a quench, you create a whole bunch of quasiparticles all over the place, and they interact, and the entanglement grows everywhere at some constant rate. But that's certainly not what we're seeing. That's certainly not what happens in these simulations, because we have a very specific quasiparticle content at the beginning of the simulation, and in fact no entanglement is produced until you have this collision. So that's kind of what helps us to get to the simulation times that we have in the first place. If this is a quench, we wouldn't have been able to get as far as we did. So I'd be interested to know if there's still
like
an
when you make
advantage.
this jump in the entanglement once the collision happens, right there probably there is some free streaming. I don't know. I just wanted to make this comment.
Yeah, no, it's interesting. I haven't looked into that. Maybe there's, I'd be interested to know if there's an advantage in this particular case where it's not a quench. Yeah.
Okay, thanks.
Or not a uniform quench anyway.
But just come back to some simpler models where your technology could be used. You're saying that you could also you could take your technology, which is pretty amazing, and you could, for example, just compute scattering in some model where you just have one vacuum. You could cook up some model where you just have one vacuum.
Sure.
Maybe the lightest particle above the vacuum, and you just scatter this.
Yes.
Two particles, and then you don't even have to go to some very large times. You just need to wait until these particles collide and separate, and there's not going to be, as long as you don't go to too much energy, you don't going to see any oscillations because nothing accelerates. And this way you will be able to map out the S matrix, and you could measure, like, it is going to be amazing because nobody has ever really measured. I mean, we know that, as you say, the wave function separates into several sectors, and but nobody has ever seen it like in an actual quantum mechanical computation, how you start with a wave function which only has two particles, I mean, apart from perturbation theory, and you follow it through this very complicated region, and then it emerges and it has all the sectors where you have 2 particles, 4 particles, and whatever, maybe 3 particles if you don't have a symmetry. I think that would be, if you're looking for something juicy to do, I think that would be pretty instructive.
Right. Well, Pedro also mentioned this the last time I gave this talk, and I think it is a very interesting thing to do. I don't see why we can't like extract S matrix elements also by taking a limit of large wave packets where we go closer and closer toward momentum eigenstates. That's in principle possible too, and it's much easier, as you point out. There are lots of complications to do with having this false vacuum that you don't have to deal with if you don't have it. Like.
From what you're saying, it looks like you can just do whatever you want. You just have full control over these systems.
As long as you can characterize, as long as you can find a good green tensor for your quasiparticle, whether it's topological or not, then you can construct these wave packets, and you can try to do these simulations. You can construct them with some initial momentum. Since they're not confined, they won't accelerate toward each other. So you have some initial momentum, you send them flying off toward each other, and they collide, and you look at the outcomes of that event. And indeed, we did a simulation like that to do with this true vacuum bubble nucleation. We just started with the false vacuum. We created two scalar quasiparticles, and we sent them flying toward each other to see if we could create a bubble of true vacuum. And this is what that kind of looks like, by the way. We only tried that in a very preliminary way, so I don't know where this goes.
Did this nucleate or
I don't think it did. I think it just created a stable meson type state on top of the false vacuum in this case. Because I don't think, it creates a small blue bubble in the middle, but I don't think this bubble is doing block oscillations. I think it's just breathing because the energy is insufficient.
Because that thing, the reason I'm asking is that because there is indeed some theoretical speculations, or there have been, of the kind in the standard model. I'm sure you have heard about this. Is that okay? Yeah, we live in this false vacuum, and the false vacuum has a very long lifetime. But isn't this somehow dangerous when on top of this false vacuum, some particles collide, and then maybe you could somehow accelerate the decay of the false vacuum? That it's dangerous.
Right. The LHC might be destroying our universe. Right?
but your experiment shows that it doesn't. Speed up.
It shows we're safe. Yeah.
Well, that's a nice message.
Maybe. Yeah, maybe that's what I should have told the guy who wrote a blog post about this stuff. Anyway, yeah, but this, you can, forgetting the false vacuum stuff, you can do this, of course, on top of a true vacuum, and I think it would be super interesting to see what we can do with this, even without the false vacuum setting. The false vacuum setting was kind of an interesting motivation, but yeah, as you say, but it's by no means a requirement of this framework. And indeed, I should mention again that this idea of building wave packets from these quasiparticle MPS states, it wasn't our idea to begin with. It was something that the Ghent gang, Frankfurt Strata and co put out a paper on doing this in the topologically trivial non-false vacuum setting. They looked at some scattering events, but only elastic scattering events, and they didn't try to characterize inelastic scattering. But they could have, in principle, tried to do that too if they'd worked a little harder on that. I'm not saying they didn't work hard, but
But I should say that what I like especially about your work, is that these people who do MPS, they like the typical MPS papers that, oh, well, we have this super duper MPS new algorithm, and let's try it on the two-dimensional Ising model spin chain.
Yes. And
then they invent another algorithm, again, try it on the same on Ising model. It's just, can't we do some more complicated theories and so on? And here you do really complicated theories. So
I mean, it's only minimally more complicated, but yeah, I believe Frank and co also looked at a Heisenberg chain, but, and some spin-on excitations and so on. Yeah.
Maybe we should like diabetically converge. Let's see if anybody else has questions, people who haven't asked any questions. Nobody.
Let me just make one remark that Zomologikov has a nice paper about this corner of the Ising model where you have these mesons. And you probably know it, but as usual with Zomologikov's papers, they are very beautiful. I recommend it, where he studies some effective theory for this linear potential and then makes an estimate of the various mass of the mesons within that approximation.
Right, yes, I think I know it, yeah.
I wonder if there is something we could do. Of course, that's kind of an approximation. The potential is not exactly linear and so on. But there is probably a computation one could do within that formalism that would produce some answer for this effective S matrix that you could probably compare with what you get.
Right.
In some quantum mechanics, the linear potential and so on, there probably is an analog of an S matrix there without particle production, but then you could see how far you are from that naive guess.
Right, right. Yeah, that would be interesting. Yeah, I had trouble extracting like information that I understand from that, but yeah, if from some logical's paper, I mean, but yeah, I mean, I'm sure you could get some sort of S matrix element there that you could relate to what we're doing, and if we can, yeah, so that would indeed be precisely the Ising type simulation that we did, where we saw elastic scattering, I suppose, and perhaps we could yes, perhaps we could get an S matrix element from that too. Yeah. We have some information containing the entanglement also. It's maybe worth noting because you know, the precise S matrix elements in the elastic scattering to some extent determine the amount of entanglement that's produced in each collision. It's also a function of the wave packet size, but there are some analytical computations in the appendix that John and Junyu did, which go into detail about how entanglement in an elastic collision depends on the form of the S matrix element and also the wave packet size.
Mm-hmm. Thank you very much. Beautiful talk and a beautiful paper. And yeah, let's be in touch and discuss some more.
Okay. Well, thank you very much for attending.
Thanks, Ash, and
thanks, Slava, for.
And thanks everyone for sticking around for this long talk, but it was worth it. So, see everyone next week.
Yeah. See you. Cheers.
See you, Ash. Bye bye.
See you. Bye bye.